Andrew Blake, great keynote there to get us going. So we're going to have a bit of a chit-chat now and meet actually a number of the characters that appeared there in Andrew's keynote. First of all, Andy Gordon, whose face we saw right at the beginning of that address. I don't know if Andy just wants to come and take a pew, any pew here. Let's get you up here. As he takes his place, you probably all know him, but he's a principal researcher. Also holds a chair in computer security and is a member of the Foundations of Computer Science Lab at the University of Edinburgh School of Informatics. So he's going to be in conversation with Jasmine as well, Jasmine Fisher, who's also going to come and sit right next to him. Jasmine's a researcher and affiliated lecturer in the Cambridge Systems Biology Centre and also the Department of Biochemistry at Cambridge. And completing the threesome, he's going to start a new seat here as well. Byron Cook, principal researcher and also a professor of computer science at Queen Mary University of London. And they're going to be in conversation with Peter, showing that Queen Mary University of London are out in force here today. That's where Peter is a professor of computer science, and he is now going to host the next stage of our event. So over to you, Peter.
Okay, thank you. So I'm going to have a chat with these folks here. And the subject, as we see, is called War on Error. So let me just say a few words about the subject area before we get started. So the area is called verification, and some of it's software verification. Now, this area is important and becoming more important as computers are used more and more in our daily lives, just because computers have flaws. And very often you hear about the importance of cybersecurity and things like this. And difficulties in cybersecurity often come down to flaws in the software. So it's important, but also as a research area, for the researchers to be interested in it, it has to have depth and it has to have difficulty and hold a certain fascination. And this area really has that. The difficulty can be traced back to the fundamental results in the 1930s at the birth of computing. Results by Gödel and Turing and Church, showing that certain problems couldn't be solved by computer programs. So verification has to square up to these sorts of problems. Now, that makes it sound very difficult to approach the verification problem, and yet there's been a tremendous amount of research over the years. A lot of it has flowed from research of Sir Tony Hoare, who is now here in the lab, work that he started in the 1960s and has done throughout his career. You might say the idea that a computer program can prove another computer program, we might call that Hoare's dream. And it's so difficult because of the unsolvability results of the 1930s that you might worry that, well, it might turn into Hoare's nightmare because it's so difficult. But in fact, in the last 10 to 15 years, we've seen tremendous strides in practical computer science, many of them coming from Microsoft on this problem. And so with that as backdrop, I'm going to now ask some of the key figures who've made these advances, how they've done it, and their view of the subject as it's evolving. So I'm going to begin with Andy. So Andy Gordon, as was mentioned, he was one of the early people in the lab, and he's invented several important formalisms, ambience, SPI calculus, and another one, ambient logic, which has been very influential. And he got into verification early in the Microsoft lab. And so Andy, would you just offer a few words on the kinds of programs you verify, how you got into verification,
Sure.
and so on?
Sure, thanks Pete. We've focused on the question of looking at cryptographic software. For example, like internet protocols or the kind of software that runs on secure coprocessors that can secure banking transactions. Now, these are, as Pete says, you've got to kind of have a passion about the intellectual questions, and these protocols turn out to be incredibly subtle to get right. I mean, there's famous examples of like 5-line programs in this area that were used for a long time, and then sort of 15 years later, devastating flaws were discovered in them. So it's very hard to get these things right. So I've worked with my colleague Cedric Fournet here, and with the team at the Microsoft INRIA Research Center in Paris to build what I think we could say are world-leading tools for verifying the actual implementation code of crypto software. I mean, a notorious problem that you have is that people build tools and can verify abstract specifications of protocols, and then it turns out that the code you actually ship has got bugs in it that were different. You know, there's a mismatch between the spec and the actual implementation. So our goal has been to verify the actual code, prove security properties of that. And we've built one tool that works on reference implementations written in F# that Andrew mentioned, and we've done some big reference implementations of standard internet protocols and found some glitches in them. And more recently, we've been looking at C software. It turns out that most of crypto protocols are actually written in C, and so we've been working with students on building tools now that are publishing at conferences this year that can verify at least small protocols. And we haven't been able yet to scale it up to really big production protocols, but we're very confident we'll go there. And it's a nice area to work on because we can make a lot of a lot of advances in collaboration with universities and publish at research conferences. But at the same time, cryptographic aspects touch a lot of Microsoft products. So along the way, we found lots of bugs in Microsoft products and in specs and shipped some code to help prevent these kind of errors. So it's been a lot of fun.
Okay, great. Thanks, Andy. So, so next, Jasmine Fisher has worked on, well, not exactly programs, or maybe they are programs. Jasmine works in computational biology, and she's bringing verification to bear, and she's also making her own models, and she has a neat phrase she's coined called executable biology. So Microsoft's a software company. It might not seem immediate that they're going to be working on biology, but with the broad kind of point of view you've got in Microsoft Research, you've got spokes going off into various of these other areas, and very exciting things are happening in the meeting point between computing and biology these days. So Jasmine, how about a few words on your work?
Okay, so I think the main idea is that we're trying to use formal verification methods, just like we're using this kind of method to try and figure out whether certain mechanisms, hypothetical mechanisms in biology, are indeed consistent with what we actually find in the lab. So we try to automatically verify that indeed these are consistent, and by doing that we gain new insight into these biological systems. And this is obviously something that saves a lot of, this directs the next experiment and highlight what are the next experiments that need to be done and verified experimentally. So this obviously saves a lot of time and resources. This is on the one hand. On the other hand, when we are using these kinds of verification methods like model checking, we can also query the system. We can check whether specific properties hold for those systems. Only when we're talking about software, we are checking whether we would like to see whether we can prove or disprove that a certain property holds for all executions. In biology, we're talking about different kind of properties. We're talking about more of the features of the system, like levels of proteins and genes and cell signaling. So we are, I think the point being is that we're trying to probe into the cell's machinery and figure out what's the program of life, so to speak. And I think it's very powerful.
Okay, so our third panel member beside me is Byron Cook, and Byron has worked on the static driver verifier when he was in Redmond, which is a very prominent tool, and he's worked now in Cambridge. He founded the Terminator Project, and the Terminator Project it attacks. There's one of the fundamental problems of the 1930s is called the halting problem. Can you write a program that tells whether another program halts on all inputs? And this is Turing showed in the very beginning of computer science that this wasn't soluble. And yet, Byron Cook here is attacking that problem, him and many colleagues. So, Byron, would you tell us about some of your work there?
Sure. So what we've been trying to do is we know that the halting problem and also actually just the question of asking properties of infinite state systems is undecidable. So what we've tried to do is to characterize certain kinds of programs that maybe we could do something with. So we've looked at device drivers, bits of aircraft software, software that's used like in things like Mars rover or things like that. So very low-level bits of code, and then we're trying to develop more general techniques that can automatically prove properties of those classes of programs. And with a particular focus on programs that manipulate the heap and then programs where we're asking them, they may be running forever, and we're going to try and ask questions about what kinds of things they will eventually do.
Yeah, thank you. So you see there's the word failure up here in the subtitle. I think this goes back to, so when Needham founded the lab, I've been told he wanted to found a lab where people worked on difficult enough problems where sometimes they failed, or else you're not working on difficult enough problems. So now maybe we can put our panelists on the spot a little bit. Andy, have you got any prominent failures to tell us about?
Oh, maybe. So, so I was one of the first guys in the lab, and Roger certainly was encouraging us to take some risks, and I'd been told if all his projects succeeded, then he'd failed. Tony Hoare was a consultant, and he went out to Redmond and came back with this quote from Bill Gates that really was confrontational for me, because I'd been an academic and I'd been used to the whole doctrine of having a sort of formal specification that you would then turn into code. And Gates had said, one document, it's the source. You learn everything there and you know everything there. So what he's saying is that, as far as engineering is concerned, the source is really what matters. Forget any sort of formal specs or all that sort of stuff. So, so we felt put on the spot, so we thought, let's see what we can do. So there was so Microsoft was working on this .NET runtime that eventually got released in 2000, and it had this bytecode verifier that was critical to the security of it, and it effectively was a fancy type system. So we thought, why don't we sort of build some tools to look at the source of this and verify that it's entirely secure, and that therefore there won't be any sort of viruses that can attack .NET. So I've barely been able to speak about this in public because we toiled away. We felt sort of gun at our head, to get this thing proved, and we didn't manage it. I mean, in the end, we got a POPL paper, which is a nice sort of consolation because it's kind of prestigious. But in reality, we really wanted to be able to verify the code. But in the end, we gave up. On the other hand, it got Bill Gates off Roger Needham's back. So, it's never a bad thing to do your boss a favor. And at the same time, Don got really deeply involved with the .NET people, and that led to his doing generics, and then eventually led on to F#. And at the same time, we also, so it was a failure, but it was also a success. So we got really in with the .NET folks and with security folks in the company, and then they started coming to us. And hey, we persevered from source code, and eventually built these tools I mentioned that can analyze C now and F# for vulnerabilities. So
okay. Now, when I was a graduate student, I remember reading a phrase where computer programs are amongst the most complicated things we've ever seen, and that's why they're so difficult to get right. And yet maybe their complexity might be dwarfed by biology. And so I don't know if you have failures to tell us about, Jasmine, but given this complexity, Jasmine never fails, okay. Given this complexity, how do you do it? How do you approach this problem?
Well, I agree with you that most often is the case that indeed biological systems are more complex than any man-made system, but more complex, more reactive in nature. But you have to remember that the whole motivation and goal to do these kinds of modeling and analysis in biology is different than in engineering. So if the grand challenge in engineering is to eventually verify the whole system or the whole program, we're not there yet in the sense that we don't have a whole organism model yet. We don't have a whole worm or a whole fly. So we can only look on very specific pieces of the system and choose manually what is the level of abstraction that we would like to look at. And by doing that in such a small scale, so we bypass the complexity by looking on smaller pieces. And so far it's been very successful because from our perspective, from the biology perspective, the minute that we increased the knowledge that we had of the system before we did the modeling work, we got something new, and so far it's been working very well.
What size of organisms or portions of organisms could you accurately model now, do you think?
So now we are dealing with, it depends on the system. So in some of the system we're focusing just on 6 or 7 cells. In an organism that has about 1,000, which is just one system of the whole organism. But in other systems where we're looking more on the tissue level, we can go up to a few thousands of cells. And we have some of our tools actually scale to that amount of cells. So it's pretty...
What's the analogy with error, so a computer bug? What's the analogy for you in your...
So I would say that we are sort of looking for the bugs in these cell programs. So we would like to know how do we get these errors, because if everything goes normal and everything is fine and everything is under control, the problem is that in disease we have these kinds of bugs in the cells program. And the whole idea of these executable models and analysis is to try to create these computational models that mimic aspects of the behaviors that cells are actually executing. So if we can find those bugs, we can basically identify what are the errors in the execution of the program going in the direction of a disease versus a normal development, for example.
Okay, now Byron, so you have the temerity to take on the halting problem. So we're speaking of failure now, so I'm sort of thinking, Byron, you must be doomed to failure, right? So first of all, do you agree with me that you're doomed to failure? And second of all, whatever your answer is, how do you deal with it emotionally?
Well, I don't accept failure, Peter. Yeah, I mean, it is doomed to fail. So, I mean, if you look at my research goal, it's to build a tool that can prove termination of any given program, and clearly I won't be able to do that. So, I mean, technically what I've done is I've changed the game a little bit. So it's acceptable for my tool to say, yes, the program terminates, no, it doesn't terminate, or I don't know. Yeah. So, I mean, one way to solve that problem would be to make a tool that just always says, I don't know. And the game is to make that threshold higher and higher. Mm-hmm. And so, I mean, there have been many failures in the sense that when we first built, we set out as a goal to build a termination prover that could prove termination of Windows device drivers. And in the early days of that project, it failed in the sense that if the program used heap at all, it would fail. If the program had concurrent execution, it would fail. And if it used low-level bit masking, it would fail. And that actually is every device driver, right? So, so we could build a few specialized device drivers that didn't actually exist so that we could say we had done something. But then from there, for each of those problems, then that led to the new research question. So basically, every time I fail, then that becomes the new thing to solve. And that's where we go from there. So it'll never end.
So does this experience where you're having some success in the face of unsolvable problems, do you think we have the right notions of unsolvable problems? Is there some rethinking to do there or something?
So I think as a community, if you look at the big advances like in automatic program verification or automatic formal verification, there are the rethinking in our community of MP versus P and undecidability. So nowadays, effectively, P is equal to MP. It doesn't matter that maybe they're not technically equal to MP, but effectively they're the same. And that actually is undoing a lot of education that you see in computer science. So a lot of people with deep computer science backgrounds have a way of thinking that really needs to be undone. So you need to think of P as effectively equal to MP, or undecidable problems as effectively decidable.
Okay. I look forward to understanding that with the new computability theory. Okay, so now we're going to turn to the future, where these folks see research and verification, in particular their own kind of research going. Maybe they'll paint a little bit of a picture for us. So again, we'll begin with you, Andy. In verification in general, or as it's related to security, how do you see things going?
I see two challenges. One is quite theoretical, the other is quite practical. So on the theoretical side, in this area of crypto software, there's actually a bit of a divide between what the cryptographers, who are mathematicians, see as what needs to be proved, and on the other side, what the computer scientists, the formal methods people like me, are currently able to prove. We're really sort of two different communities, but just recently we're starting to come together. So a challenge would be to take we'll be able to build like verified implementations of some substantial internet protocols that are actually verified against the mathematics that the cryptographers use. So there's a paper that makes a nice advance of that at the crypto conference, the cryptographers conference this year, by Gilles Bart and what's his name, Santiago Zanella. And we're very happy to have him coming as a postdoc. We managed to recruit him, so we're hoping to make some progress on that. And very briefly, on the practical side, a big thing that's happening at the moment is web applications, and they're being standardized, and HTML5 and JavaScript are they're like the core of the web. They're going to be really important for Windows 8 applications, and I think what we'll see in the next few years is people from our research community building tools for reasoning about such web applications. And we're quite confident that the verification techniques that we have for F# programs could be adapted to JavaScript eventually to be able to do proofs about the web platform and show web applications secure.
Okay, Jasmine, same question to you. What about the future?
Well, I'm not a formal member of the software verification community. I'm more of a guest. I kind of came to visit 8 years ago and never left. But I think from more of a biologist perspective, I think that there are two main challenges in that realm of things. So one thing would be that we really need to create these tools and means for biologists to do these kinds of work. So these means really user-friendly kind of tool, biologist-friendly for non-professional programmers that will be able to do this on a daily basis and in between to integrate it into the lab, everyday lab work. And on the more long term, I think that this is part of this transition that biological science is taking towards more of an engineering kind of science. And I think this is what we call executable biology. We try to make the major challenge is to try and make this kind of new emerging field a more mainstream technique in biological and medical research. And in order for that to happen, the first one has to happen. So we need to provide the tools, and this is a major challenge, I think.
Okay, Byron, same question to you.
So, I mean, there's always the problem of scalability and precision running on concurrent, proving concurrent programs. I mean, I'd promised that P was equal to MP, but we actually have to make that so, yeah. But I think another thing that's come out in my work with Jasmine, I've noticed is that biologists have a really different viewpoint on the tools when they're using these sorts of tools. So when applying our tools to software, strictly, often the developer just wants to know, is there a bug or not, and please show me the bug. But in the application to biology, actually, it's a biologist who's asking maybe deeper questions. So they don't want just a yes or no answer. They want more information about counterexamples when it's not true, and they want information about why something is true when it's true. So it's less of a yes or no sort of thing, and more an analysis or sort of richer information about the system that's being analyzed. And I don't really know how to do that very well right now for Jasmine. So that seems like an area for future work. So
one of the amazing things that's happened is where this verification enterprise has gone from a lot of fantastic pencil and paper work to these folks are all now talking about tools. And I'm wondering about the relationship between tools and the theory. I don't know if this is true, but would something like the following be a good way to view research in the area? That we have the experimental method, usually we have that in science. Is the tool and running it against things like, is this an analog of the experiment that tests our theory? Or how do you think of how to organize your science as you do it? If any of you want to pipe up with an answer, it's okay.
Well, that's right. I mean, you find you find examples of programs that don't work, and then try and build tools that can check them. And I suppose, in principle, you should go and find more examples independently and see whether your tools work against them. And we try and do that. I'm not sure if, as a community, we're completely perfect.
So I guess verification is learning a lot from building the tools, and I can well imagine Byron and Jasmine working together. Not only are we applying verification to biology, I presume you're learning a lot about verification via that attempt.
I'm learning a lot about biology. Yeah.
I guess that's a pretty good result.
Yeah,
isn't
that's
it?
right. Yeah. One thing that's interesting is that the techniques that you can use when trying to prove absence of bugs in software and the techniques you can use in the models that come from biology are actually quite different. So things you could never get away with in normal software will actually work in biology and vice versa. So that's quite interesting. What you see in our area of sort of software verification is there are now competitions and there are multiple tools being run against each other. So that's one way now that we're sort of sharing results. That's a little bit different than just sharing ideas in research papers.
Okay, so I think it's time to draw the panel to a close. So we didn't want to finish on any big note. Rather, we wanted to show how the area of software verification, it has importance and growing importance, but it's a deep area, and it's an area where there's lots of fascinating things going on, as illustrated by the comments from my colleagues here on the panel. So, well, thank you for listening.
Cheers, guys. Fascinating stuff. So, Peter O'Hearn there with Andy Gordon, Jasmine Fisher, and Byron Cook. So, there's a really nice kind of flow through the concepts